Let's look at another definite integral. Here we have the integral from 0 to pi over 4 of sine 2x cosine 2x. Now, you can look at this for the first method as a u du, because we see here that we have basically the derivative of sine of 2x, but we're missing the 2 from the chain rule. So what we can do is write the sine 2x and then put in the 2 here and adjust for it. So now we have the u du. So this is just add 1 divided by the new power. So we get 1/2, then of course sine of 2x quantity squared divided by 2, evaluated from 0 to pi over 4. And then of course the 1/2 times the 1/2 is 1/4, and then we get sine of pi over 2 when we multiply 2 by pi over 4. And then we get sine of 0. Each of these squared, so we get 1 squared, which is 1, 0 squared, which is 0. So basically 1/4 times 1, which is 1/4. Very straightforward. Now, in some problems, we change limits when the substitutions are a lot more complicated, but here they're very straightforward. But you certainly reserve the right to do that. I just think that it's good to be able to work with a method that pushes the problem forward quickly. Now, say for instance you have looked at this problem a little bit differently, and this will come up, especially in your physics classes. You remember the double angle formula from trigonometry, that is sine of 2 theta is equal to 2 sine theta cosine theta. So you're thinking, well, that's basically the double angle formula, but we don't have the 2. So this is basically what sine of 4x times 1/2. Notice without the 2 here, we need to compensate for that. So the beauty of this problem is that you can think of this in terms of a trigonometric identity. And now the actual substitution is simpler. We basically have what we need. We know the antiderivative of sine is the negative cosine, but we don't have the 4 by the chain rule. So we put in the 4 and then compensate for it. So again, we'll have 1/4 times 1/2, which is 1/8. And the antiderivative of sine is the negative cosine. So now we just evaluate the negative cosine between pi over 4 and 0. Now in order to get rid of the negative, that is, not have to worry about it in the fundamental theorem, I'll go ahead and extract it here. And so then we have cosine of pi, that is 4 times pi over 4 gives us a pi. And then of course we'll evaluate at 0, 4 times 0, 0. So we have cosine of pi minus cosine of 0. So cosine of pi is -1, cosine of 0 is 1. From the fundamental theorem, we have -1 minus 1, that's -2. So the negatives absorb, we have 1/8 times 2, which is 1/4. So of course we get the same answer. But what's interesting about this problem is that when we do integration, definite integration, the theorem says where big F is any antiderivative of the little f, so to speak. So when we look at this problem here, we get an antiderivative that looks like this. Okay? That is an antiderivative of this function here. Now when we approach it a little bit differently, we get an antiderivative that looks like this. So this is the big F when we approach it this way. This is the big F when we approach it this way. Now, of course, we know from the mean value theorem that these functions differ by a constant. But with trigonometric identities, it is often very difficult to see that. You have to do quite a bit of algebraic maneuvering to show that. So what I'm trying to say here is that it doesn't really matter how you approach an integral as long as you do it legally. And certainly what you want to do is approach it in a way where there is confidence. So like I say here, standard, add 1 divided by the new power, or if you just got the trig identities right on the tip of your brain, double angle formula. And we are done.